Thanks very much. That's way too loud. So our current fascination with mass extinction is historically somewhat anomalous in the history of geology. As many of you will know, for most of our history, we didn't actually think that mass extinctions existed. Cuvier did, but they sort of disappeared from our intellectual zeitgeist until about the mid to late 1950s, but certainly since 1980, they've been a major focus of work not only by paleontologists, but by many other geologists as well. And this is documented in part by the databases that paleontologists, including Jack Sepkoski, as shown here, have used to chronicle the existence of these events. And you see the sort of 5 canonical mass extinctions here. A more recent compilation by the Paleobiology Database with John Elroy as head is shown here, looking at generic data from the marine record. And you can see that this compilation shows a lot more variability within the diversity of marine genera than was shown in the preceding family level database, but nonetheless the major events still stand out fairly clearly. And that leads to compilations like this. This is a catalog using analyses by Sepkoski, by Elroy, and also by Richard Bombach, noting their estimates of the percentage of marine diversity losses during the 5 canonical events. And this and many other studies have led to the view by most people that there's really something different about mass extinctions from what happens during so-called background times. And many years ago, Dave Jablonski wrote a paper looking explicitly at this issue of the distinction between mass extinctions and background events. And I think most people looking at mass extinctions operate on the assumption that there's something not only quantitatively as well as qualitatively distinct about these biodiversity events. And in doing so, we look and in fact, the focus of most of this session, as well as the succeeding technical sessions later in this meeting, will look at, in a very detailed way, various proximal causes as well as ultimate causes for these various events in a way that would have made Aristotle very happy, I imagine. And so some of these, the ultimate events, or ultimate causes of these events are very well known. Those will be detailed by many of the other speakers here. There will be much discussion about flood basalts, about other kinds of volcanism, about the possibility of impact, about the correlations, as seen here from a paper that Gerda did in 2012 on the correlations between anoxia and flood basalts and oceanic plateaus. And here's another compilation looking at these correlations. All of you will no doubt be happy to know that I'm not going to talk about any of that. This is from Dick Bombach's 2006 paper in Annual Reviews of Earth and Planetary Sciences, in which he used the Sepkoski database as updated to catalog the percent extinction in the stages from the Cambrian all the way up to the present. And you'll note that there are a number of mass extinctions that stand out, 18 in fact, in addition to the canonical ones that we're all used to hearing about. And there's another way of looking at this event, and this goes back to a question that was initially raised by Dave Raup back in the 1990s, and this is whether or not the great mass extinctions really were qualitatively as well as quantitatively distinct from background extinctions. In 1991, in a paper in Paleobiology, Dave proposed what he called the kill curve. He suggested that what we think of as the great mass extinctions are simply part of a distribution of events going from occasional events that have very large magnitude, the Primo-Triassic, a bunch of things of middling magnitude, the KT, and then a bunch of smaller events, which are the tail of this curve, or the other events, or could be seen as the other events on Bombach's list of 18. And none of this is taking into account the fact that in the Cambrian, variability was actually quite high, largely because diversity was so low. So the question that I'm going to pose today is, did the cause of these events actually matter? This should annoy most of you, probably. The argument I want to make, or I'll try to make here, is that what's actually interesting, given some recent papers that look at the duration of these events, may be the way that ecosystems fall apart. That attempting to develop a general theory of mass extinctions that focuses on the causes is misplaced. Because what actually unites these events is not the generating mechanism, but rather the fact that once you insult the ecosystem sufficiently hard, the ecosystem collapses in a similar way, whatever the cause. The first paper that I want to mention is this paper that came out in PNAS, I think in January or February of this year, by Burgess and Sam Bowring and Shuzhong Shen from the Nanjing Institute and MIT, in which they continued the studies of the duration of the Permo-Triassic mass extinction as recorded at the Meishan locality in South China. And I call your attention to the extinction interval shown here in red or in gray, using a combination of ash beds that are shown in black here that bracket the boundary, as well as carbon isotope data and statistical analysis of extinction patterns. They estimate the extinction interval for the Permo-Triassic to be 60,000 years, plus or minus 48,000 years. That's pretty quick. And the paper that we published in 2011 suggests that this is, in fact, not simply a local or regional signal, but rather a global signal. Similar results came out from the Cretaceous Paleogene boundary. This is a paper by Paul Rene and colleagues looking at sections from Hell Creek and other sections up in Montana, where they get similar estimates, and there's additional unpublished data that suggests that the duration of the KT, at least as recorded in these events, could be as short as 20,000 years. If we look at data for the late Triassic, the Triassic-Jurassic event, this paper by Blackburn et al., and Paul Olson and Sam and Troy Raspberry and a bunch of other people, looked across the Central Atlantic Magmatic Province, which is figured prominently in discussions of the end Triassic event, and their estimate for the extinction interval is about 5,000 years. For the Hangenberg event, this is a paper by Paul Miro and Terra Nova. The Hangenberg, these ash beds bracket the Hangenberg shale. This is not quite as tight as the others, but the estimate here is, again, 50 to 100,000 years. This is a much smaller biotic crisis than the other three that I've mentioned, but in all cases, it looks like these events are really short. And the estimates of the duration are limited more by the depositional record and the quality, or not the quality is very high, but the resolution that we're now capable of with particularly radium-lead single isotope zircon geochronology. Most of our conceptual approaches to looking at mass extinctions have assumed either that we wiped out primary productivity and then something happened, or we wiped out the top of the food chain for one reason or another, and all sorts of bad things happened. What I want to suggest, though, is that the similarities in the rates of collapses of these different events suggest that there's a pattern of the collapse of these events, which is not simply driven by the loss of either the bottom or the top of a food chain, but includes the distribution of extinctions across there. So let me distinguish, as ecologists have for many years, between primary extinctions and secondary extinctions. The primary extinctions are largely due to abiotic effects during a mass extinction, whether it's Ebola, volcanism, pick your favorite cause. It sort of doesn't matter for these purposes. Whatever that extrinsic cause is, that removes a certain number of species within a food chain, or trophic species. That then leads to secondary cascaded extinction subsequently. One of the things that we don't know, and we've in fact never really tried to estimate except in very recent events, is what the relative proportion of these primary to secondary extinctions are. I suspect, I can't demonstrate this at the moment, I suspect that in fact many of the extinctions are likely to be secondary rather than primary. But knowing at least the relative ratios of these would be very helpful. So we'd like to know what the percent of total diversity is that's lost due to primary extinctions versus secondary extinctions. If most of these extinctions actually are secondary, then the triggering event itself may be less important to the dynamic of the whole process than network structure and associated biological effects. So let me use a quick analogy. These are images from the NOAA website of the US blackout in 2003. This is 20 hours before the blackout. You can see Long Island and New York City. This is 7 hours into the blackout. New York City is almost dark. This blackout extended all the way up into Toronto, all the way out to Michigan and Ohio, covered a huge section of both Canada and the United States. It was largely due to a software bug in a control room in Ohio. And because it was not clear how to manage that collapse, although after the effect it was clear that it should have been easily contained, it cascaded into failure of grids across the northeastern United States, and it was largely stopped by people who knew what was happening in Maryland and Pennsylvania and New England, literally taking their state out of the grid, not because they knew what was going on, but simply because that was the only option that they had. So about 80% of the previous load was lost. I mention this because it turns out that from a mathematical point of view, the problem of understanding these food webs is exactly the same problem as understanding the nature of the power grid. I'm briefly going to discuss a couple of ways that people do have of looking at food webs, but in doing so, I want to be clear that our current understanding of network structure and dynamics is not yet sufficient to solve the problem either of mass extinctions or power grids. DARPA has currently put a little over $5 million into a collaboration of some colleagues of mine at the Santa Fe Institute who are trying to solve the power grid problem and develop an approach to networks that will allow an understanding in a formal sense, a mathematical sense of how power grids operate. If that works, the same system actually will be applicable to food webs and other systems. So there are three ways, or a couple of ways we can actually, I think, move forward as this research in network structure moves forward. The first is trying to resolve the significant patterns of species extinction during the events themselves, rather than simply comparing before and after. Isotopic approaches, I think, will help with this, particularly in highly expanded sections. This is, again, a graph of the Meishan section. In southern China, at a place called Panglitan, we have a vastly thicker section. It's about 10 times as thick for the same duration of time as Meishan. These sorts of sections with appropriate statistical techniques may actually allow us to begin to understand what the dynamic of ecological collapse is during the events. Although I put good luck up here. Whether or not we can actually resolve time to this level, I think, is unclear. An alternative is looking at pre-existing food web structure as a basis for discriminating extinction patterns. This is a paper from Jennifer Dunn and Conrad Lavandera and their colleagues looking at the Messel Lake in Germany. This is a lake and a forest food web. This is about a 500 and some odd taxa food web here, simply to make the point that we can, in fact, reconstruct food web structure quite well, both in the modern record as well as within the fossil record. And doing this sort of stuff both before and after these events will give us some insights into the nature of the structure of the web and how that web has changed as a consequence of the extinction. But ecologists also have tools for taking data like this, which is a purely topological web and has a number of severe limitations, and looking at which of the links are particularly important in the structure and dynamics of the food web. This sort of topological approach focuses largely on three aspects: species richness, connectance, which is the way the species are connected to each other, and a quality called structural robustness. Jennifer and Neil Williams, in a paper in 2009, examined various techniques for looking at structural robustness, and these are the sorts of things that we could begin to apply to the paleontological record as well. There's also more recent attempts to use a Bayesian approach. There's a paper by Eklof et al. That was published in 2013 that uses a greater variety of ecological data to assess the risk that various species are under during events. Applying this sort of an approach to the fossil record may also yield probably even greater insights than a topological extinction, a topological food web model would. So all of these are approaches to looking at the internal dynamics of mass extinctions. And that is in addition to my major point here, which is that the highly resolved geochronological data of the duration of 3 of the so-called great mass extinctions and at least one of the smaller but still significant biodiversity events suggest that all of these, the only 4 good data points that we have, indicate very rapid collapse of the ecosystem during these events. And that, I think, suggests that the bulk of the extinctions may not be primary rather than secondary. That's purely a guess. I have no data to support that. But I think gathering that kind of data is just the sort of thing we need to do to begin to understand the internal dynamics of extinction processes and perhaps learn something useful for our own future. Thank you.